So we will be covering a very interesting topic in linear algebra today, which is going to be vector projection. You will appreciate its importance as we go along the lectures, but today we start lightly from foundation and we then just continue onward. So I'm importing the libraries and I'm defining this function that you're used to, okay? Now, what is this vector projection? So assume that we have this vector A and just assume this point B. Now, imagine that you want to draw a vertical line from B onto vector A, okay? So the closest distance that you can do this is by drawing a line from B to A that happens to be a vertical line. Okay, so that would give you the closest distance between B and A. Okay, now just assume we did that, we would be basically coming at some point on vector A if we draw this orange line, which is a vertical line from B to vector A. Okay, now from our previous lectures, you know that you can always, if you have a vector and a scalar multiplied by that vector would yield basically another vector, but in the same direction. Okay, it would be exactly in the same direction. So there is this beta value you can assume that if you were to multiply it by your vector A, it would point directly up to the point where projection from this point B was on. Okay, so you got your vector A, you got this point B, you can draw a vertical line from B to A. Okay, that would basically be a section of the vector A, from here to there. But at the same time, you would be also having a scalar that can do the same thing, like select a section of vector A. Okay, let's just expand this a bit further. Now assume that instead of point B, there is a vector called B, this green vector. Okay, so we are having this green vector, and the orange vector is exactly that. It's the vector that basically is, going from point B vertically, going over vector A and the beta A that we just discussed. Now from vectors adding adding and subtracting, this orange vector, if you were to find it, you just easily can get it by subtracting this beta A from B. Okay, so that's how you do, when you want to add or subtract vectors. So vector B minus this vector beta A, the red vector, would yield the orange vector. Okay, so this is basic vector addition subtraction rule. All right. So now let's look at it from a linear, that was geometrical representation of it, yeah? So now if we go and look at this formula here, now the shortest distance from the point to the A, vector A, is a vertical, okay, I need to comment that, go to the A, to the vector A, okay? So the orange line, we know that the dot product of two orthogonal vectors should yield 0, okay? So because the orange vector and the red vector, or vector A, doesn't matter, yeah? Vector orange is vertical to vector blue, okay? Think of it like that. So vector orange, this vector, which we said it was B minus beta A, is orthogonal to vector A. So if we had a dot product between these two, we would get 0. And that is exactly highlighting that. So it's A transpose, like basically A, dotted with B minus alpha B, B minus alpha B, beta, sorry, alpha beta, yeah, which is this orange one. Yeah, so blue one dotted with orange one should give us 0, okay? Now, if we do a bit of playing about and expand the formula, so we will have A transpose B minus A transpose A beta equals 0, all right? And then we are just going to try to calculate B. Now, beta. Now, beta is a scalar, okay? So all I've done, guys, here, all I've done here is basically moving one of these to the other side of the equation, and I'm trying to see how I can calculate beta. In other words, all of this was about calculating beta. So if you have a vector, green vector, and you have a blue vector, and you want to project a vertical line from end of this vector onto the blue vector, okay, we knew that there would be this beta value that which is a scalar that if multiplied by vector A would give us a vector of that sort of magnitude. Now this really, the red line is the projection of vector green on vector blue, okay? So the red line, yeah, the red line beta A is projection of the green vector on the blue vector, okay? And beta gives us exactly that. It gives us a scalar that we can multiply by A to find the projection of this other vector onto vector A. And we just found the formula. So if in future I ever tell you, we got a vector A and a vector B, project vector A on vector B, yeah, how are we going to basically do it? All you need to do is to dot vector A by vector B and divide it by the vector A dotted with itself, okay? And then it would yield you the beta. And obviously, if you multiply beta by A, then you get projection of B on A. So all this was about how to calculate projection of a green vector, this B, on the blue vector. And that's the formula, blue vector being the A, all right? Let's now look at it, from a linear algebra sense. Well, like in Python, technically. So let's have these two vectors. So we have vector A, okay, and vector B. All right, so that's our vector A, that's our vector B, okay, and I'm just going to um, plot vector A first, yeah. So that's our vector A, right? So that's the vector. And I'm going to plot vector B, okay, and I'm going to just plot it like this. I've just used these two dashed lines and all just to show you that this is vector B and this is vector A. So just think that we want to, let me just do them together now here. So the orange one and the blue line, yeah, so orange and blue, just like the picture that I used. So if we want to project this orange one on the blue one, how are we going to do it? We call back our formula beta, which was A transpose dotted with B divided by A transpose A. Okay? So if we do this, let's just run it. Okay. And I'm gonna just call beta. Okay, so we got the beta to be 0.44827. Okay, whatever that value. All right. Now, to get that projection, the projection of orange, all we need to do is to multiply beta, which is a scalar, by A. So beta A, which is going to be a new vector, which is the projection of the orange and the blue, we're going to call it beta A. All right. So now I'm going to plot all of these together. So plt.figure fixed dpi equals 100. That is to give a high resolution to the plot. Plt.plot, plot in vector A, okay, and I'm choosing color blue. Plot in vector B, okay, plot in vector B, and I'm going to be plotting now the projection, okay, and just bear in mind that just for the origin, I'm using the origin of the other two lines because they're from the same origin. So beta A, you know how we are plotting vectors now, okay? And I've just used the label, yeah? So beta. And here I'm projecting beta A, or I. All right, so let's just run it. Maybe if we run it first, then it would be better. All right, let me reduce this for the moment. Okay. I was hoping that it becomes smaller in size so I can show you. Okay, I need to reduce the size. Okay, so I'm just plotting the projection of B. So that's beta A 0, beta A 1, giving me this point, and the origin is from 0, 0, 0. Okay. Now the green line, which was the line that was showing us the projection point, it's the vertical line. We are not really interested in this at the moment, okay? We are not really interested in this green line. Rather, we are interested in the projection, the dashed red line. As you can see, the formula works. So we had the blue vector, we had the dashed vector. We wanted to project the dashed blue vector onto the main blue vector, and we exactly did that by using this simple formula, calculating beta and then multiplying beta by the main vector. All right. Okay. And then the way we basically express this, like in terms of notation, we are projecting the vector B on vector A. So this is how you write it. Projecting vector B on vector A equals beta A, everything that we covered so far. And we now know how to calculate beta. So this is the most important formula that I want you to memorize or remember or learn, basically. Yeah. And obviously, I want you to also just remember orthogonal vectors dot product always yield a 0. Yeah. So here, what have I done? I'm dotting A with this vector, yeah, B minus beta, and I'm just rounding it to prevent computer rounding errors, yeah. And obviously I will be getting a 0. Very important, guys. The dot product of two orthogonal vectors yielding a 0, and that's how we used it to prove this formula for the projection. Okay, well, I hope you have enjoyed it, and I'll see you at the next lecture.